Well, good afternoon, everybody, and welcome to the second of today's webinars from Smart Vision. Today's webinar day with Smart Vision, and that means we're going to be doing 3 webinars. Thus far, we've looked at correlations in SPSS. Now we're going to look at decision trees, and then later on at 3 o'clock, we're going to be looking at regression and an introduction to linear regression. This one's focusing on decision trees. My name's Charles Quinn. I'm an analyst, data analyst working with Smart Vision Europe. I'm joined online today by my colleague Rachel, who'll just be making sure that everybody's logging in correctly. If you haven't joined any of these sessions before, you should be aware that the sessions are recorded, so you can listen to them again. We also have a YouTube channel of previous sessions recorded. There was some slideware, most of it's demonstration, but we'll email a link to you afterwards to download the materials after the session's ended. And if you think it's particularly useful or relevant for colleagues who are unable to join us today, it may be possible for us to arrange a rerun of the session. It just depends on if you can get enough of them together. The best thing to do if you do want to go down that route is just to send us an email or something like that. Reach out to us in some way, and we'll see if we can arrange that. Now, with regard to asking questions, there's a lot to pack in. I don't always check the chat facility as I'm going along. We ask you to use the chat panel. My colleague Rachel will probably field a lot of the questions, but we are used to following up afterwards. You can, of course, just send us an email afterwards if something occurs to you. Or if you're thinking about your own work and how you might apply decision trees to that, we'll be happy to follow up with you offline after the session's ended. If you don't know who Smart Vision are, we're a technology company. We're a gold accredited partner to IBM and also to a company called Predictive Solutions and DataRobot. And we specialize in advanced analytics, data science, AI type technology, and statistics, though we also work with open source technologies such as R and Python. We're made up of a veteran team of individuals who've 15 to 30 years of experience working in the advanced predictive analytics industry. I first started working for SPSS in 1995. Worked for them for a long time until the acquisition by IBM, and worked with IBM, and then worked with SAS Institute, if you've heard of them, and other analytical software company. And that basically means we've got quite a lot of experience of applying these types of techniques across many different applications in many different vertical sectors, whether it be in the commercial world or the non-commercial world. And certainly decision trees is relevant in pretty much every sector I can think of. As we get onto the subject of decision trees, you might want to bear in mind where decision trees actually lies within the world, I guess, of what we would call predictive analytics or data science, if you prefer. And there are different types of modeling families, if you like. One of the most common is the world of prediction, sometimes referred to as classification or propensity modeling. And this is very much where decision trees belongs, which is, trying to figure out who's most likely to respond to an offer, or who's most likely to defect from a service, or which patients are going to be readmitted to hospital within a certain period of time, or which assets are likely to fail. And we use historical data, of course, to try to model that and create predictions around that. Other types of predictive analytics include things like cluster analysis, where you don't have a target field. There's no one specific thing that you're trying to model, but rather you're trying to group together similar people, similar patients, similar customers, similar events to create sort of categories or segments, if you like. There's association and sequence analysis, where you're looking at what combinations of things tend to co-occur. Sometimes that could be products which are purchased within a store, or it could be assets that tend to fail, or component parts which tend to fail together, or even things like health comorbidities which tend to co-occur more often than normal. And lastly, we have time series, where we look at things like demand or a time trend. We're trying to extrapolate out into the future to forecast things like website hits or visitor numbers to an attraction, or revenue for a particular product, or rainfall or something like that over the next day, month, quarter, year, or so forth. So we're very much in the first world, the first of these categories here, which is the world of classification prediction, propensity modeling. Though it has to be said that decision trees, you don't have to necessarily be building a decision tree to create a predictive model. Decision trees are really good at delivering just insight in a really intuitive and a visual way. I would say that they should be used very widely within survey research. If you're doing surveys, a questionnaire type analysis, decision trees work really well within that area, and you'll see why when we actually get to demonstrating it. So decision trees are used extensively and widely within the world of predictive analytics and data science, and they can be used to build profiles. It's one of the first things they do. They're very good at profiling individuals or employees or clients or patients or customers and saying who is most likely to answer a question in a particular way or who's most likely to fall into a certain category. And in doing so, what they do is they find segments or groups within that body of data, which are often really interesting. These are often key behavioral segments. Lastly, they can be used in themselves to generate a predictive model. So they can be used predictively to actually say, what is the likelihood that somebody's going to, I don't know, renew a subscription to their Netflix account, or people who are likely to recommend a particular service, or people who are likely to default on a payment, or people who are likely to defect from a particular subscription that they have, for example. And they can be expressed as a series of hierarchical rules, which is good because it means that rather than using formula, like logistic regression, you often get quite a complex formula out, which will generate a probability value for you. Decision trees are just a series of rules saying, if somebody is male and they're aged over 30 and they live in this region and they've bought this product, then there is an X% chance they will fall into a particular group. And as a result of that, it's less abstract, I guess, than a lot of formula-based predictive modeling. And it also means that these rules can be converted into commonly used languages like SQL for database scoring, or even plain English language, or SPSS syntax, or whatever it is you're working with them. Now, decision trees are really popular. And one of the reasons is because they're very visual representation of models. So the kind of modeling about tiers. And as a result of that, they're relatively easy to understand. So often when you're a student and you're starting out on your AI course or your undergraduate data science course, one of the first things they introduce you to is decision trees, because it's quite a gentle introduction to the world of predictive modeling. Okay, so with that in mind, let's look at an example, a worked example here. This is a really famous data set which is used a lot to describe and explain how decision trees works. If you ask people, what are the most important factors determining survival during the sinking of the RMS Titanic, most people can guess what the three most important factors are. If you ask in a room, as I have done many times, a room of 30 or 40, 50 people, what do you think are the most common factors that drive survival? They're all going to come up with the same three factors, which are, of course, whether or not they're a male or female, whether or not their age, particularly in terms of whether or not they're an adult or a child, and the class that they were traveling in, whether it be first class, second class, third class, etc. So that's fairly straightforward. And you'll often get people saying, well, this isn't telling me anything new because I knew these factors were important. But what decision trees do is they tell you, in many ways, which ones are the most important. When you ask people, say, well, what's the most important? That's a different question. And the way in which a decision tree would typically answer that is to run some sort of analysis or test. In the case of one of the most well-known decision trees, it uses a really old statistical test known as the chi-squared test. And the chi-squared test is associated with crosstabs, if you've ever done any crosstabs. So if we did, for example, a crosstab of gender, sex of a passenger, against whether or not they survived or not, and we're looking at the column percent here, we can see it's 73% of females survived compared to only 21% of males. A chi-square test basically produces a value and says, what's the probability of getting a result as extreme as that, assuming that gender made made no difference. You know, if you lived in a universe where gender didn't make a difference to people's survival on the Titanic, how often would you get a result as extreme as this, where 73% of the females survived, but only 21% of males survived? And that returns a probability. And that acts in many ways as a kind of measure of what's the most important factor, because the smaller that probability is, the greater the discriminatory power that has, the more the bigger a predictor that is of the outcome of whether or not they survived. And of course, it doesn't have to be survival here. We could be using it for any sorts of target field. It could be, you know, people responding to a mailing, or people who are likely to recommend a service to a friend. But certainly here, the gender value here produces a very large chi-square value. If we compare and contrast that to our next factor, which is age, adult and child, you can see the chi-square value is much smaller, and the effect is smaller because 31% of adults survive, whereas 52% of children survive who were on the Titanic. That's not as big a difference as the 73-21% split. That's a 52-31% split in the same order. And if we look again at the next factor, it would be class of travel. So we can see that 62% of those in first class survived, 41% of those in second class survived, 25% of those in third class survived, and 24% of the crew survived. That also produces a chi-square value, and we have a significance or probability value associated with that. And if we were to rank them in order at this stage, it would probably come out something like gender, class, and whether or not you're an adult or a child in terms of the order of the importance. And that would give you an indication of which factors are most likely to be included in the decision tree in the order which they're likely to be included, if you like. So let's just look at that in a little bit more detail. If we were to build a decision tree and we were to try and enter these values into it, what would that look like? Well, let's just have a look here. This is what the decision tree, a Chade decision tree, shows initially. I'm just showing you the top of it so you can learn how to read the decision tree. The first thing is we start out with 2,201 passengers in the famous Titanic data set. There's some data sets out there that will tell you even the cabin people were staying in and how much money they spent on their ticket and things like that. This data set simply has gender, class of travel, and whether or not an adult or child. And gender is the most important factor that goes in right away because it splits the data. And it gives us a chi-square value. In fact, you can see the chi-square value here, 456. That's exactly the same chi-square value that we saw earlier on. And it's saying the probability of getting that is 0.000. It doesn't mean it's zero. It just means it's run out of decimal places. It's probably 0.000012 or something like that. So it splits the data. These 2,201 people are suddenly split into males and females. And what's interesting is there are actually only 470 females traveling, something which isn't often reflected in the movies. It's a relatively minority group within the passengers on the Titanic. And we can see it's 73% survive. Notice that it shades the larger group. That's the modal group. And therefore it says, well, if you're female, you've got a 73% chance of survival, or probability of 0.732 in this case. Or if you're male, the modal group, the larger group, did not survive, 78% chance of not surviving, or only a 21% chance of surviving. That leaves us 1,731 cases. And notice also that it assigns these groups what it calls a node number. That just means group 1, group 2, as it's going down through it. So as we add in the extra factors at this stage, it looks like this. It's a little bit more complex, and indeed, it's not symmetrical. It's actually got some sort of exceptions to the rule in here. So we see that when we split the 1,731 males, the next factor it chooses is whether or not you're an adult or a child as the next most important factor for the male passengers. And it says, well, look, if you're a male child, you have a 45% chance of survival. If you're a male adult, a 20% chance of survival. And then it splits these 1,667 cases again. So we get these group sizes are getting smaller and smaller as we go down through the tree. it says, you know, for first class male travelers, adult male travelers, 32% chance of survival. Second class, 8.3% chance of survival. Third class, 16% chance of survival. And crew, 22% chance of survival. So, you know, converse to a lot of the sort of dramatic depictions of the sinking of the Titanic, the people who had the smallest chance of survival were not adult males traveling in third class, they're actually adult males traveling in second class, where there were 168 of them, and only 8% of them survived compared to 16.2% of the third class, males traveling third class. Over in the female branch, we see that age has not been included here. And the reason why age hasn't been included at this point is because it's not statistically significant. It doesn't fall below a certain threshold called an alpha level, which the default is a p-value of 0.05. And it's basically saying that, look, age isn't important to survival if you're a female passenger. So it doesn't go in. And secondly, when it adds in the class variable, it actually groups together second class and crew. So you can see here, second class and crew are separate here. It groups them together because it doesn't make a statistical difference. Their survival rates are not sufficiently large enough in difference for them to require their own little nodes or their own little boxes. And thus, 87% of females in second class or crew survived, 97% of females in first class survived, and 45.9% females in third class survived. And that means that eventually everybody ends up, if you'll forgive the phrase, in one of these terminal nodes. That means a node where a group where it isn't split any further. And that means that you're going to end up with a probability value of survival for each passenger. And there are actually only 1, 2, 3, 4, 5, 6, 7, 8 probability values that this tree will generate for different groups. These terminal nodes generate the probability score. So when we apply this tree as a model, it's going to generate 8 probability scores for us split across all 2,201 passengers, and it's going to tell us the probability of them surviving. So you can see there, just from the insight alone, that it's quite insightful. It finds an exception to the rule. It finds groups that are not statistically different from one another, and it finds these odd little nuggets where, you know, converse to received wisdom. It was actually adult males in second class had a much lower survival rate than adult males in third class. Now, decision trees have different algorithms. They have different methods. One of the most famous is the CHAIDE decision tree. And as you can see down here, CHAIDE is actually an acronym developed in the 1980s by a guy called Gordon Cass. And it stands for chi-square automatic interaction detector because it's looking at interactions between the fields. You could have produced this tree manually just by running lots of crosstabs and kind of making note of the probability value and then stacking them on top of one another. But as you can imagine, that would take some time to do, to try to figure all that out and, you know, split gender by age and then split age by class and then split gender by class and compare that and split, you know, class by age down here and compare that. It would take a while to do that. So one of the things that's so impressive about decision trees is the speed with which they arrive at these solutions and the level of insight they provide, and the fact that the model they're generating is in fact a very visual model. So we see examples of that. Something else which is really useful about them is that you don't have to use just category fields in decision trees. You can actually use a continuous field. So you could have put, instead of just putting age as adult or child, you could have literally put their actual age, and it might have found a threshold, maybe under 30, you know, 31 to 45 and 46 and over as a split. Because what it does is actually it finds these threshold points where the differences are statistically significant from one another. So here we have people buying a financial service, 56% of them buy the service. However, when we split that by savings on investment, it says, you know, the critical thresholds are those under 4,395, where it's 28%, between 4,395 and 6,150, where the purchase rate is 48%, 6,150 to 8,000, it's 63%, and over 8,000, it's 78%. And it's doing that, it does that in a really simple way. It just takes a continuous field, a number field or an interval field, and it splits it into 10 deciles. So it effectively becomes 10 groups, and then groups those adjacent groups together. In this case, it takes it from 10 different groups, and we end up with 4 different groups instead, because the intervening groups are not statistically significant from one another. So it's really powerful in that sense. If you're just saying, you know, at what point does a threshold or change in a discount, for example, or a revenue or the price of something, at what point does it have an effect, a statistically significant effect upon an outcome? Again, very powerful and very, very easy way to incorporate that within the tree in a way that's still very readable without using coefficients or any complex formula. Okay, let's see a demonstration. Let's go out to SPSS here. I've got SPSS open. And I've got a data set here. How many records have we got? We've got 300 records, okay? And the data set is some sort of financial data set where we've got some demographic information in the form of interval variables here: age, income, number of children they have, disposable income. So look at that. Disposable income is some sort of measure of income to the number of kids that you have, a ratio of one to the next. So it ranges from, in this case, $2,500 to $59,000. And we have, you know, whether or not they're male or female, the region that they live in. What regions have we got here? We've got 4 regions: inner city, rural, suburban, and town. And we've got whether or not they are married, whether or not they have a car owner, they are a savings account owner with the bank, whether or not they're current account owner of the bank, whether or not they have a mortgage currently. And then this key field here, which is home insurance. And if I look at that, this is our target field. We want to try and understand which people have home insurance and which people don't. What is the profile of those who have home insurance to those who don't, using a decision tree? And we can even use that to predict against a data set where the people haven't purchased home insurance yet. And we wish to use the decision tree to target those who have the highest likelihood of purchasing home insurance. Something to bear in mind here is that the group sizes here are quite even, 55 to 45. I mean, that's quite an even split. It makes it a little bit easier to teach decision trees when you have that. Of course, in reality, you'll often have a target field where one of the key group that you're interested in is actually very rarely occurring. So if you're looking at things like, you know, response to an advert or something that's been shown, and whether or not somebody clicks on an advert, or whether somebody responds to an offer to become a subscriber to a service, you might be dealing with only a 1% occurrence of that. So it'd be 99% versus 1%. In which case, you're really interested in those parts of the decision tree where people have a more than 1% chance, you know, where they have a 2% chance or a 3% chance, because although it's still a very small number, it's 3 times, potentially 3 or 4 times higher than the baseline of 1%. You know, they are 3 times as likely as average. And that can be very powerful and very useful to people when they're trying to figure out, you know, who should I be making this offer to, especially if there's a cost associated with the offer. So within the commercial world, decision trees are very powerful in that sense. Okay, to build a decision tree, we're going to go to Analyze, and we go down to Classify, and we call up the decision tree module, which is not it's not a part of the base module within SPSS. It's just here as tree. Call that up. So it will come with I think it comes with SPSS Professional package and the SPSS Premium package. Or it can be, if you don't have it already, you can actually add it to your existing base package as an additional module. And it would occur simply as an extra dialog box, which we're seeing here in the menu item. And it would be enabled simply by putting a new code into SPSS, and it would unlock that capability to you. So my key target field here, the thing I'm really interested in is what's called a dependent variable, and that's home insurance. I'm going to pick up everything else except ID, because obviously ID isn't really a proper variable that we would use analytically. I'm going to throw them in, and I'm going to, you can see the method is chade. I'm going to run with the default settings at this stage and just show you what the initial decision tree looks like. And then we'll return to it, and we'll go into a little bit more detail about, what we can do to try and change the appearance of the tree and maybe get more insight out of it, and how we can use it to build a predictive model, etc., etc. So let's click OK at that point. It runs a decision tree, and the first thing happens is we get a decision tree just in the output here. I can expand it to make it look bigger, so you can see it a little bit bigger here. And you can also see it's a really small tree. Okay, it's not very many. It's not very complicated. But that's partly because there's only 300 records in the data set, and the initial default settings prevent it from building a big tree if you haven't got very many cases, and we can change that in a moment. Currently, the most important factor it has found among all of these different fields, let's just look back at these fields, look at all these different fields we had here. All these different fields here we could have used to predict this outcome. And the most important factor it has found is the number of children that people have. And it's saying 0, 1, or greater than 1. That's how we interpret this. And this is node 1, node 2, and node 3. And it's saying, look, if you've got 0 kids, then normally you'd have, on average, 45% of people would buy home insurance from this bank or sign up for home insurance from this bank. It actually drops to just under 36% with 0 kids. If they've got 1 kid, it jumps to 85%. And if they've got more than 1 kid, it drops again to 32%. So it's quite good at finding these non-linear relationships, these sort of exceptions to the rule, where it's not like the more kids you have, the more likely you are to buy home insurance. But within this group here of 110 people who have more than 1 child, it's actually split it further. It's found a variable that it can split further. And it says, well, look, if they're aged under 41 or younger, then it's only 12.3% of them would buy home insurance. But if they're aged above the magic threshold of 41 years old, then 54.7, just under 55% of them would buy home insurance. And you can double click on this tree. I'll be doing this a lot. You can double click on this, and it opens it up into its own little editor. You get your own little editor here, and you can, if it's a really complicated tree, you can zoom into it. And something which I find is useful, if you go to options here, if you click on ranges as text, sometimes people find it easier to understand these range thresholds here. If you go for ranges as text, you can see it says 0 or less, higher than 0 through 1, meaning just 1, and higher than 1. So it's something to bear in mind. Options, ranges as text is a way sometimes to make it a little bit more readable for you. Okay. Having established that, and having established that we actually only have 1, 2, 3, 4 terminal nodes here. So we only end up with 4 probability values if this tree was used to to score a data set and produce probabilities for us. So it's a very, very small tree. If we wanted to get more insight out of it, what could we do? Well, out of the procedure, well, we could go to analyze, classify, call up tree again, and we could change some of the default threshold values. And probably the first thing you would do is you go to criteria here, and you can see that we have a parent node and a child node setting. Now, if I just come back here to this tree that we saw earlier, this is this node's parent. This is this node's child. This is this node's child. This is this node's parent. So parent and child just means before split and after split, effectively. I mean, it just means that. It says, do you want to have control over, the minimum group sizes before a node is split into a subgroup, and what the smallest child node should be. And obviously with 300 cases, having a default setting of a parent node set at 100 cases, child node set at 50 cases, that's quite conservative. So we can change this. So let's change it to 25 and 15 and see if that makes a difference. Click continue and OK. Now it's rerun the tree, and you can see that because we've given it more freedom, The tree is more complex at this stage. I'm opening into its own editor. I'm zooming into 150%. Again, number of children is still the tree structure hasn't changed at the top here because that's still the most important factor. But it's now split those of 0 kids into whether or not they are currently married. So I could split it down and it says, okay, well, look, if they're not currently married, the total number of percentage of people buying the product, it's only 30 cases, is 68%, 30 out of 44 cases. And you can even split that further and still be statistically significant into whether or not they're a mortgage customer. And if they're not a mortgage customer, then it's 93% of them actually buy the product. There's only 27 cases there in that. Over here in the yes, I am currently married group, there's 84 cases, and it also splits them by mortgage customer. So here the difference is non-mortgage customers who aren't married, 10% buy the product, and those who are mortgage customers and are married, 40% buy the product. Here it looks at people with 1 child, 62 cases, and finds the threshold of disposable income that makes a big difference. And it says, look, if they have less than 14,724 in disposable income, it's 63% buy the product. If it's more than 14,724, 97% buy the product. And the same variable is used to split those with more than 1 child. It says, look, if they have more than 1 child and the disposable income is less than 14,724, only 6% buy the product. And if it's more than 1 child, then it jumps to a massive 91% buy the product. So it's very good at finding all these exceptions to the rule. And you can also see within here, we can have some control here. We could say, okay, show this as charts to me, where red indicates that no, they haven't bought the product, and blue indicates that yes, they have. So you can see just effectively, it's almost possible to imagine it as a filtration device. It's like you've got colored sand at the top here, and it's just trying to create the purest groups it can, purest red and purest blue, using these variables and these splits within these variables. Or you can mix them together and have both the charts and the numbers shown. Okay, so what happens if I just go back? Can I even make it even more richer than that by really, really changing the criteria? I could go down here to 10. I'm getting really down into the weeds here. 10 and 5. Continuing okay. Let's see if does that make a difference? Yes, it does. Actually, it adds in the variable age, which we hadn't had before. So it's just allowed it enough to add in another variable age. Now, there's a danger here. You don't want to make the group sizes too small, because if you make them too small, you end up doing something called overfitting. And overfitting means when it's too specific to that sample, you end up with splits which aren't really, all right, they're statistically significant. This is 0.016. But, it's not very reliable as a model. And that means that when you come to applying it in the real world, you often find that with an overfitted model where you've allowed it too much freedom, that it doesn't work as well. The accuracy isn't as great. So what I'm going to do is I'm just going to test this model. I'm going to go back. I'm going to change it back to the previous criteria here of 25 and 10. I think, 25 and 15, I think I had. And I'm also going to take the time here just to point out that you can restrict the tree depth and say, I don't want you to go more than 3 levels deep. That's one of the rules you can enforce in it. You can, within the shade algorithm here, you can say, actually, I'm going to insist that you don't work at a 5% level, you work at a 1% level. And I can even change the chi-square statistic. Pearson is the classic one. Likelihood ratio is a slightly more updated version of that. But I very, very rarely find that it makes any difference changing the two. But, if you wanted to be really careful, you could go for likelihood ratio. It's slightly more accurate, I would say. And something called, you should never really switch off, is adjust significance values for using Bonfer-only method. That means that it takes account of the fact that you're doing multiple statistical tests, and it adjusts overall to make sure that the tree is significant, still statistically significant, taking into consideration the number of statistical tests that you're doing. So they're not completely if you like, independent of one another. It actually adjusts the probabilities to say, look, you're running a lot of tests here, and you really should be careful. And so Bonferroni is a standard method that's used for that. If I want to test the tree, though, I could click on validation here. And there are different types of validation. One which I'm going to dwell on here is simply to split the data, the 300 cases, into a 50-50 split and say, I want you to build the model on, that's called the training sample, on 50%, and I want to test it on the 50% that are that haven't been included in the model. So if we held back half the cases, how accurate would the model be? Well, we click continue and OK. Let it run that. Before we get to that last bit of output there, you may notice in this previous tree I ran, where we had, we were allowing it down to quite small splits. You'll see at the bottom here, it's telling me how accurate that is. That was 95% to 79% accurate. So that's pretty good. You'd be thinking, well, this is a really good model here. 95% of the no's have been correctly predicted, and 79% of the yeses have been correctly predicted. Whereas if we were taking a random approach, the best you could hope to predict accurately was be 55% by predicting everybody to be in a no group. If you predicted everybody in the no group, you'd be 55% accurate. So this is obviously a lot better than that. How well did this do, though, when we ran our second classification tree here, or our third classification tree here, decision tree, where we asked it to split the data? Well, what it does is it produces a smaller tree for us because it doesn't have enough cases. Only has 353 cases, as we can see here. And then it shows us what that tree would look like if we applied it back to the data set. So let's just double click on that and have a little quick look at this one. So let's see if we can zoom in here. This is the training tree here. So it's saying, oh, 46% in the yes group here and 0% in the yes group here. What happens when we apply that to the test tree down here? No, it isn't the same. So it's not 0%. It's actually 17% and 30%. So this is when we apply this tree structure, if you like, and we superimpose it over the 147 cases that were left in the test sample. Do we get the same percentages, if you like? We're getting the same sort of split among the groups. Well, there's some small differences here. Does it affect greatly the overall accuracy of the model? Let's have a look. Because we look at the bottom here, now we have our classification table, which has been split into training and test. And it's saying, well, actually in the training group here, it's 77% accurate in the no's and 88% accurate on the yeses. And weirdly, on the test group, it's actually more accurate. It's 91% to 80%, which is overall 86%. That's unusual. Okay, I'll say that straight off the bat. You wouldn't normally expect that. You would normally expect to get to find that the test group is less accurate than the training group. It isn't an error. It's just luck more than anything else. I mean, I could run the procedure again, and it should choose a different random 50% splits. If I click it again, run the procedure again, you can see now it's different. It's 90% accurate in the no group in the training and only 63% accurate in the yes. Whereas down here, it's 87% accurate in the no and 54% accurate in the yes. A difference of 78% accuracy versus 72% accuracy. So bear in mind that you can get lucky even with a training test split, but this is a way to give us an idea of how stable the tree actually is and how good a model it is, if you like. Okay, one thing I would point out here is that the reason these are getting assigned as no and yes is simply on the basis that if whichever is the modal group, whichever one has more cases, whichever one's greater than 50%, it gets predicted to that group. So if somebody was predicted to be 49.999% likely to be a purchaser of the key product, i.e. insurance here, they would still be predicted to be no. And if somebody was given a probability of 50.001%, they'd be predicted to be a yes. So you shouldn't get too hung up on this classification table here, especially when you're dealing with a target variable that has a target group in it, which is really small, a really small group, like a 1% chance of somebody, buying this product. Because you'll probably find that nobody ever gets predicted to be yes, because you're asking the tree then to find groups where you know, they're going from 1% baseline chance to more than 50% chance. And as a result of that, people tend to have a different method for different methods for assessing, you know, are there useful bits in the tree that we can use. So let's look at that. I'm just going to click back here to validation. I'm going to switch off the validation and say, no, let's just go back to building the whole tree. And what I'm going to do is click on categories up here. If I click on categories up here, I can actually identify that the key category is the yes group in home insurance. That's kind of my target category within the target variable, the target within the target thing. These are the groups I'm really interested in, and that will produce extra output for us. If I click OK at that point and run that, here's our tree again. And you can see you're getting this extra table here. This is called a gains table. And the gains table is basically listing which are the best nodes for predicting the yes group. And it says node number 7, which has 32 cases, and that represents 10% of the entire sample, 10.7%, because we've got roughly 300. We got 300 records, of course, and 32 is about just over 10%. And it's saying, you know, if everybody belonged in that group, if you could find everybody in that group, you would actually find 23% of the people who bought home insurance within just that group. What node is that? Well, we can count along here. There's no, you can see there it is, 32 cases. 100% of the people in here are all predicted to be people who buy the home insurance product, and therefore the response is 100%. The second best node is node number 10, which is down here, 93%. You can see there it is, the response group. How many cases are in that? It's 29. What's that? It's just under 10% of the cases. How many would we find in there? Well, we would find if everybody belonged to that group, we'd actually find 20% of the home insurance people. So adding these two together, if we just use those two nodes, to predict or to identify the people who are home insurance, would actually find 43.7% of them in that group. And in fact, if you go to decision trees here and you go to the output, you can go to the statistical output here, and you can see these extra stuff. You can ask for cumulative statistics. Cumulative statistics. Continue here. Click OK. It runs it again. And it gives you the cumulative gain. So this is really this bit here. It's saying, look, you're gaining for the first 3 nodes, you're finding 66% of the people in the target group. So you can see how that would be really useful, even if the probability was less than 50%. You know, you could use a decision tree to say, look, I've only got a 1% response rate to my marketing campaign, but using this gains table, I can find the first, you know, that the first 4 nodes will find me, I don't know, 20 or 30% of the people that I'm trying to target within that group. So that's why it's useful. It's just listing out which groups or which segments within the decision tree find as many cases in the target group that we're interested in. If you want to see that graphically in output here, that is shown as a curve. There's different types of curve. There's a gains curve here. You can get a node plot. The gains curve is a very common way to show this. And scroll down here. There it is. And it's saying, look, let's say I only have budget to target 30% of the customer base for my offer, you know, to try and get people to buy home insurance. If I could target the best 30% of the customer base using this decision tree, what proportion of the naturally occurring proportion of people who would buy home insurance, what proportion of them would I expect to find? Well, if I look that up, it says you'd find 60% of them. And if I could increase my budget to target 40% of them, then that would get up to nearly 70%, 78% maybe of the people. So this is basically a representation, a graphical representation of that table. And it's a way for us to help us find how to help us work out what proportion of the base we would have to target if we were working with the decision tree in this manner. We're trying to build a predictive model. would we have to target in order to find all of the people in the key group, whether they be people who cancel their subscriptions, patients who are likely to be readmitted to hospital, or machines which are likely to break down, or whether it be people who are likely to purchase, or recommend this to a friend, whatever the key outcome is. Okay, so getting near the end here, we've kind of worked our way through a lot of this. What happens if we actually wanted to, let's go back here to switch some of this off. What happens if we wanted to get it to save predictions for us? Well, we can actually see the save predictions here, because I can actually click on save and say, show terminal node, show me the predicted value, and show me the predicted probabilities. Click continue and OK. And I can run that, and you can see it actually produces this. It says this guy here belongs to node number 7. The predicted value is 2. What's 2 refer to? It refers to the yes group in the home insurance. So I would predict them to be a yes responder. The probability of them being in the 1 group, that's the no responder, is 0, because 0% of people in node 7 were in the no group. And the probability of them being in the yes group is 1, because 100% of them in node 7 were all purchased home insurance. Whereas down here, people in node 8, we predict them to be a non-home insurance buyer. There's a 93% chance that they're in the non-group, and only a 7% chance they're in the yes group. Okay, so is there a way for me to get it to produce these values for me? And apply them to a data set where the people haven't had a chance to buy home insurance yet. Maybe they haven't been offered it yet, or maybe there are people who who are part of the customer base who haven't been targeted yet, or whatever. Well, yes, we can. So what we do is we can call up the decision tree again that we just ran. We can go to save here. I'm going to switch off this. I don't really need this. And instead, what I can do is I can say export the tree as a model. So I can export this tree. I've already got one here called insurance. I hit save at this point. It says, do you want to replace it? And I click continue. Yeah, I want to replace it. I want to rerun it. And it reruns it. It just basically does the same thing again, but this time it's saved that little file out. And what I'm going to do, is I'm going to open up a new data set here. And it's called insurance scoring, which is if you wanted to score. This is called applying the model. It's called scoring the model, or scoring the data set. And this is a very similar data set of, another 300 cases or so. Yeah, another 300 cases, different customer IDs. And, it's already been saved. I'm going to delete that. I want to apply that model to that data set. Notice that this data set doesn't have the home insurance product in it, because, of course, they haven't been offered the home insurance product. We want to apply the previous tree saved as a model file to this current data set. And to do so, you can do this with any predictive algorithm pretty much in SPSS statistics, and decision trees are no exception. I'll be doing the same thing when we look at linear regression. If I go to utilities and go to scoring wizard, I can search for this little model. There it is, insurance.xml. Hit select. And then go down through the wizard, and it says, okay, here are the fields I need, because these are the fields which are in the decision tree. And if one of them is called a different thing, let's say it isn't called disposable income, let's just say it's called extra income, or, net income, or something like that, or instead of disposable income, I could actually map it across and say, look, this maps to the disposable income field here. So it's quite good. It's not even fussy, if you like, about having exactly the same field names. You just need to tell it which ones match up with the model fields. Hit next. This is what do you want me to produce? Well, I say I want you to produce the predicted value, i.e. whether you're yes or no, or 1 or a 2. I want to see the node number. I want to see the probability of the predicted value, or I'll say, show me the probability of a selected category, which will be category 2 here, which is the yes group. What's the probability if they're in the yes group that they will buy home insurance? Hit next at this point. Score the active data set. Hit finish. And it just basically runs it and says, okay, I predict these guys all to be 2s. Here's the probability values associated with them. They've been sorted in order here. I could sort them. Let me go back and sort this in customer ID order. So you get more natural look to it. There you go. So probability of being in the yes group, 70%. Probability of being in the yes group, 10%. Probability of being in the yes group, 7%, 100%. At this stage, if you were working with the data, you might say, okay, well, I want to go to data, select cases, and I want to select everybody where the selected probability, let's say, is greater than, I don't know, 0.485 or something like that, because that's the that's the kind of baseline level of probability of being a home insurance buyer. So you could actually say these are the people I want to select for my campaign, and you could then export that data set out from SPSS in whatever format you wanted to for selection. Something to bear in mind is that I've only talked about one type of model algorithm there, which is the CHAID model algorithm. Let me just go back to the insurance train again, and we'll just do a quick comparison, a compare and test. Let's go to decision tree again. Let's just do home insurance. I'll just quickly reproduce this so you can compare and contrast this using a different algorithm. I'm going to go to criteria again. I'm going to change this to 25 and 10. I'm just picking these numbers out of thin air. This is what the CHAID model looks like. You've seen this already. There is another method here called exhaustive CHAID. It's just a more intense version of the CHAID algorithm. It's actually it actually goes in. It looks at every possible, well, nearly every possible permutation of merging the groups together. So it's more about merging than splitting. Does that produce a different tree? I suspect it'll look very, very similar, just glancing at it here. Yeah, I generally don't find it makes a big difference. What does tend to make a bigger difference, though, is if you use a non-statistical technique such as CRT, which stands for classification and regression tree. This was developed by a guy called Jerry Friedman in about 1979, I think. And this is a non-statistical method, so the machine learning method. And it creates binary splits in the tree. It only splits them into twos each time. It produces a very different tree. How accurate that one is, 94 to 73% versus 95 to 79%. So, it's worth playing around with them and seeing which one gives you more intuitive results and more accurate results, if you like. The CART is well known as CRT is often called CART. It's a well-known algorithm. It's well documented, and it's one which gives good results. So it's definitely worth trying out. The last algorithm here is Quest. I tend not to use it very much. I don't find it's a very useful algorithm, but it was a modification of CART because CART was originally quite slow, and that was a kind of a modification of it. Okay, what about finishing up here? What about a data set where we're not trying to predict somebody who's likely to buy a product, but rather we're kind of predicting people, who have some sort of rating scale or some sort of attitudinal data associated with it? Well, I've got a little HR survey here. I can just click open that, and this time we've got a 3-category target variable. It's not a 2-category, but 3-category target variable. This is one of the reasons why it's really useful for things like surveys. This is a survey, and we're asking people in the HR survey here, how long do you think you're going to remain an employee in this anonymized HR survey? And we can see there are 3 groups: leave within 2 years, leave after 2 to 5 years, or remain at least 5 years. So these are the 3 groups that we've got. And we can build a decision tree using that instead. Let's see what are the most important factors in that. Let me just send that up in there and quickly pick these other variables. Again, I'm just going to give it a bit looser set of criteria, let it go a bit deeper, 20 and 10. Using the CHAID method, 3 categories this time. Click OK. It produces a very shallow decision tree we can see here. So very wide, very shallow, and we can zoom in to 150%, and we can see that that the 50% of people will remain at least 5 years. And if we were looking at what is the single biggest discriminator between those who say they'll leave within 2 years versus those who remain at least 5 years, it's answering the question, what do you think of the attitude of the senior staff? You might find, for example, and this is an occasion where ranges as text is a better way to view it. And it says basically, if they rate them as fair or less than fair, then 82% say they'll leave within 2 years. And if they say higher than good, which is very good, then 74%, 75% of them will remain at least 5 years. And then we can see how that splits down into the other factors like working hours, holiday entitlement. Find the exceptions to the rule that we talked about earlier on. Is there an exception to the rule here where people say, look, 82% remain at least, will leave within 2 years. Can we get that number lower? Well, yes, it says if they think the working hours are better than fair, and if they think the holiday entitlement is better than fair, then that number drops to 26%. So we find these exceptions to the rule. So again, we might want to use our charts here to see where the big splits are, or we might want to combine them with the percentages, so we can see the charts and percentages. Very, very useful way to profile individuals within a survey, rather than necessarily doing a formal predictive model. But it's just another example of how flexible decision trees are. Okay, so that finishes up there. Let's just talk about a couple of other things. Drivers of satisfaction. You saw me basically this is kind of a satisfaction survey we were looking at there with HR surveys and asking people how long they're likely to remain an employee. But we can use this in other types of satisfaction. We can use it to demographically profile people. These are people here or in an ethnic minority group. If we wanted to try and say what factors seem to create clusters of people in non-ethnic minority and ethnic minority groups, it can be quite a useful way to do that. We can see that a lot of them in the custodial group here, and some of them in the clerical group here, but they tend to be aged between 25 to 45. And things like interpreting clusters, I find that if I do cluster analysis, it produces segments for you, but it's hard sometimes to make sense of the segments and try to figure out, what are the differences between them. So if I make the cluster group my target variable in the decision tree, it tells me that cluster group 4 are people who like to buy beer and canned vegetables, whereas cluster group 3 are people who don't buy beer but do buy wine and don't buy canned vegetables, and so forth and so forth. So it's a good way to just interpret any sort of segment and try to figure out where are the hot spots, or where are the groups that are coalescing around certain factors or subgroups within the data. You should be aware that for SmartVision customers, we have free online training materials that are available for the SmartVision customers for free, or available to purchase if you're not one of our customers. We do provide a lot of consultancy in this area and in other analytical areas, and a range of different consulting services there, whether it just be 1 to 2 days or 3 to 5 days or longer. You can source your software, your SPSS software, directly from us, of course, and we can assist with the piloting and implementation of analytical tools, as well as providing formal classroom training or a mix of classroom and consultancy, or even informal bite-sized training split over time and developed and delivered virtually. But we generally offer no strings attached advice to all comers, whether or not you're a customer of ours or not. You can just come and ask us and we'll try to help you out. And if you are a customer, we provide track technical support services around things like decision trees and the IBM SPSS product line, so you don't have to go to SPSS for technical support. We do hope you found that useful, and we look forward to logging in again. The next session we're going to be looking at 3 o'clock is an introduction effectively to linear regression. So do feel free to log in if you're interested in attending that. Thanks very much.